Hi everybody, welcome back to this channel. Today we're going to talk about the more general approach to solving the circuits, which includes the controls of the node voltage analysis and mesh current analysis. Most of you learned in this 201, and I assume you did not get a very solid foundation in 201, so I hope I'm already on the safe side. So I'm going a little bit more detailed than necessary to some of you maybe, if you had a very solid understanding of the node voltage analysis and mesh current analysis. So today there will be four topics or four clips. The first two will cover the node voltage analysis. And the node voltage analysis, I will break this into two parts. The first part would be the relationship between the node voltages and element voltages. And although this is quite obvious to some of you, I hope this will clarify any of the sort of confusing spots for some of you. And the second part of this lecture would cover the how we can formulate the node voltage equations. And the third part, or the third and fourth parts will cover the mesh current analysis. In my experience, most students feel like a mesh current analysis a little bit more confusing than the node voltage analysis somehow. But anyway, so the mesh current analysis I will first address. That's in the third part of the lecture with the third video clip, and they address the relationship between the mesh currents and the element currents. So we have mesh currents, which very kind of abstract to some of you because they are not really the actual physical current you can measure, right? So it's kind of fictitious. But I will build a solid foundation, at least somehow rigorous, to relate those mesh currents with the element currents. And so that may take a little bit longer time for a third clip. And then the last one, we will see how we formulate the mesh currents equations. Okay, let's look at the node voltages and the element voltages. Right. So normally, let's see if the reason we have this node voltage analysis is because we don't really want to solve a lot of equations, right? So let's see if you have E elements, right? So each element will have a voltage and a current as unknown. So you really have two E unknowns, right? That requires two E equations. If you just write all these element constants, right? So in that case, that's a lot of equations to solve. And on the other hand, if you, let's see, we have only n number one nodes, right? The n number one nodes, and for in this case we have n independent the TCL equations, right? And also, and in this case, if we can only solve n equation, that's a lot less than the 2E equations. Okay, and also we have, if we have the mesh current, and in this case we're going to have E minus n mesh currents, or independent meshes. So independent KVL equations. So using the node voltage analysis, we only need to solve n independent. And if we use the mesh current analysis later, we will introduce in this lecture, we'll only need to solve E minus n. So that's a lot less number of equations we need to solve simultaneously compared to just write the element constants for the system. Okay. So let's see, the first thing is what this really node voltage is. The node voltage is, normally when we see a voltage, we will have two points, right? So we mark plus reference mark on one point on one node, and we mark the negative or minus reference mark and the other node. And then we label that. But for the node voltage, we choose a one reference node, and then we only label. So this V sub 1 and V sub 2 are node voltages, are the so-called node voltages. And now we don't really have plus minus sign here anymore, but we do have this reference node. And what this really means is this. So this, what if I draw this using the reference, using the node voltage nodes and the node voltage notation, what I actually mean is I'm having this node voltage V sub 1 is basically I'm marking plus sign here, and then the negative reference mark and the reference node, and the voltage between these is the V sub 1. If you remember, when we talk about the element constraints and the connection constraint, we talk about voltage rises and voltage drops, right? So basically from node 1 to the reference node, the voltage drop is V sub 1, right? That's what this node voltage really means. And the second one here is the same thing for the node voltage V sub 2. And from node number 2 to the reference node, the voltage drop is the node voltage V sub 2. Okay, that's what it really means. And then the next question is how these two node voltages, they are related to the element voltage. Here, the element, let's see, we have impedance Z, and I labeled the plus and minus sign. Just arbitrarily, I just show as an example. You may, in the circuit, you may label plus minus the other way, but in any case, in this case, we will see how this VZ is going to be related to the V sub 1 and 2. So the thing here is we're going to use the KVL. You see how each lecture is built upon the knowledge we have in the other lectures. So if you are not quite clear about this, go back to lecture number 2 to get the how you write the KCL equation, KVL equations, right? For KVL equation, if we recall, there would be 3 sort of different flavors, right? So you could add all the voltage rises equal to 0, or you add the voltage drops equal to 0, or you can write the equation. One side of the equation is the sum of the voltage drops, and the other side equation would be sum of the voltage rises. So in this case, let's see, arbitrarily choosing the direction. I'm looking at this mesh. The mesh I have here is I have V sub 1, and V sub Z, and V sub 2. These 3 voltages, they form a mesh, a loop, right? I'm trying to write a KVL equation following the direction, the clockwise direction I chose, and I am using the third flavor. Okay, the third flavor. So in this case, if following the clockwise direction from plus to minus for V sub Z, that's a voltage drop, right? So now I need to write the voltage rises, the sum of the voltage rises on the other side of the equation. So let's see, the sum of voltage rises, so let's see, go from negative to positive for V sub 1, that's a voltage rise, right? Because from negative to plus, and from plus to negative, that's a voltage drop. So from negative to plus, that's a voltage rise, V sub 1. Although we have 2 other awkward ways, technically correct, of saying the voltage rises and drops. And from negative to positive, you could see the voltage drop is negative V sub 1, so on and so forth. Go back to lecture number 2 if this really kind of confusing you, okay? And so the other one is the from plus to minus, that's a voltage drop is V2, but we need a voltage rise, so I need to negative V2. So this is voltage rise. So this is rise, and this one is rise. So I have 2 rises add up on the other side. So this is how actually the element constraint is related to the node voltages, right? If you want to memorize the node voltage, the element voltage always equal to the node voltage on the plus sign of these elements minus the node voltage on the negative reference mark of the element voltage. I don't really like you to memorize, but that's how you should be able to really sit down and spend 1 minute writing this key value equation, really understand. Okay, this is very important. I'll stop this clip and start another one, and we talk about how we formulate the node voltage equations.